So in this video, I'm going to be discussing the concepts of relativity. And so in AP Physics, there are in IB Physics, there are two aspects to relativity, both of which are dilations. And so there's a dilation of time and a dilation of length. And so these are two things I'm going to be talking about. And first I'll talk about time and then about length. So the reason that a time dilation occurs, well, there are several ways of explaining it. First, if we're looking at it just from a purely conceptual way, it's because we live in a four-dimensional universe. So because there is length, width, height, and time. So that's 4 dimensions that we live in. And so as we're traveling through space, and especially at higher speeds, we warp everything around us, including time, which is like shown by Einstein's space-time. And as we're warping that, we're going to change the perceptions of our time passing versus the perceptions of for example, a static object's time passing. So that's one way of explaining it, but another way is the classic train car example. So we have a train car that's standing still, and there is a mirror at the top, and then there is a laser, and then there's a little laser beam receptor. So it takes the light travels that distance when the train car is staying still. But when the train car is moving, and it's still made up of all of the same exact components, then the light is going to have to travel like so. It's going to have to travel a greater distance to get from A to B while the train car is moving than while the train car is standing still. So since it's going to take light more time to travel the same distance, that's where the time dilation comes in. So at higher speeds, it's going to take the time longer to travel that same distance. So that's where we get our time dilation. Now let me just grab a paper towel here to erase this. And then I'm going to talk about length dilation. Now this one's a lot more simple and a lot more intuitive, because what it really is just how light hits our eyes. So say that there is a rectangle, and this rectangle is standing still, and then there is a little human. Yay. So the light is going to bounce. Say there's a little sun. It's going to bounce off of this side to our eyes, and then off of this side to our eyes. And so we're going to be able to see very easily that this is this perceived length when both we and that object are static relative to each other. Now, however, if this object were to be moving, so say for example it moves from here to here while we're observing it, and sorry, I didn't mean it to be that small, it just kind of ran out of room, but if it moves from here to here, then initially the light we're going to get is going to be from this beginning, from the first side of it, but then the second light that we're going to receive is the second side. So it's going to appear shorter because, for example, let me draw a slightly better diagram, because nothing's going to move. That would have to be moving faster than the speed of light, because if it moved from this point to this point in the time that it took the light from here to hit us and the light from here to hit us, then it would actually appear switched, and so that can't really happen. So if it moved from here, say, to here, then we would be seeing this. It would only appear that long, because at first this would hit us, and then as it moved, the other light would only be able to hit us from this point on the rectangle, and so it just appears shorter. And so that's really what time dilation and length dilation are. It's just because objects are moving so quickly, either light has to travel a longer distance, or light isn't able to travel from a light source to the object back to the observing object, or for in this case the human, in enough time to do it equally from both the end, or the end and the front of an object, and so it appears shorter because it's moving and there's effectively lag in the light.